means for an agent to be secure, governed, and observable. So this is the high-level agenda today. We have a lot to cover, but we'll start with agents 101 with a basic understanding of what agents are. So with this, I want to launch the first poll to get a sense of, a lot of people have actually built agents and have at least heard about this buzz, but do you really understand, what agents actually are? So let's launch the first poll.
So guys, you can see a poll in your window, hopefully. And please, we would like to know, yeah, I can see some answers. Great. We're going to have this poll for around 30 seconds, and then we can continue. Great, great. I'm ending the poll now, and yeah, Anand, you can continue.
Perfect. So I can see a lot of variation, and let me also share the results. So majority is none of the above, which is actually the correct answer. But the first one is all LLMs are agents as they can act and perform tasks, right? That is not actually true because we'll shortly explore why this is not the case. LLMs cannot do things; they can just think about things. Second one is LLMs by default have access to real-time information. That is also not true because again, LLM is just a model. What it needs for real-time information is something called a tool. And the third one is LLMs are good chatbots because they can remember past conversations. Again, a blanket statement is not good because they need a specific thing called memory, right? And we will explore these components in a lot of detail today. So why LLMs alone fall short, right? So remember what LLMs are. These are just models which have trained bases a lot of data and have come up with very intelligent capabilities to think in a very nuanced and very nice manner about a lot of things under the sun. And they can also follow instructions, right? That's how they have been trained. So they can think effectively, but they cannot do anything, right? They are like humans who are just stuck to a chair, who can think about the world, but cannot go out and do things with hands and cannot make actions. They're limited by what's available in their training data, right? So they do not have access to real-time information. If I ask what's going on, let's say with Indigo in India or with Trump in the world, they do not really know what's happening today by default. And again, there's a single inference basis the user query, and there is no memory or any context management as such, right? So it's just a model. You're giving it a query, you're getting an answer. That's the scope of LLMs, right? So it's very important to understand this differentiator, which is where agents will actually come in, and we'll talk about it. So what they need is to be able to perform actions like making API calls. They need to be able to connect to real-time information, and they also need to have a managed session history, which is basically memory, which can allow them to talk to you over multi-turn conversations, keeping all the context in mind, right? And giving you a very nice, coherent answer. So what we need effectively is to augment these LLMs with certain capabilities, right? So this is where retrieval comes in, where they can actually retrieve, let's say real-time information or even information from a particular document base that you have internally, probably proprietary in your company or even personally. They need access to tools, which is basically enabling access to external information, external things out there, right? Databases, articles, lot kind of things. And finally, memory, which they can actually refer to if they are going for long conversations, right? So it's not just a user prompt LLM and output. They need access to a lot of these things, which is where this concept of augmented LLM actually comes in, right? And loosely speaking, very loosely speaking, this is how you can think of an agent. An agent is nothing but LLM plus tools, right? Plus prompt, right? Which is actually defining how that LLM should think and how it should behave. That's the minimum requirement for an agent, right? And a little bit more strictly speaking, this kind of a agentic framework should be able to iteratively think over problems in a very deep manner, right? So that's something we will probably touch upon when we see the hands-on. Now, if you look at this, it's probably clear to you what memory is. It's probably clear, what we mean by retrieval. We are retrieving information of a database that you are referring to, but what are tools? And why do we need it? So, for example, if you ask, what's the weather like in Boston? The LLM needs to have real time information, right? So, what it needs to do is effectively do a web search and probably access a weather API out there, which can give it the answer because obviously it does not know the answer directly. So, it needs to hit that API, it needs to get that information, and it needs to refer to that, wrap it up in a nice answer, and give it back to the user. Multi-turn chatbots is another use case, right, where it needs to write to a memory or a database and it needs to read from it in subsequent turns, right, and so on. So basically, what tools are helping it do is perform certain actions, right, in a nutshell. And when you think about tools, who is actually executing that tool? So just think about this. How does the model even know that there is a tool out there that it needs to access? So before MCP came out, right, and we are not going to talk a lot about MCP, but I just want to give this reference that before MCP came out last year in November 2024, the application code needed to have this information that, okay, these are the tool definitions, the schemas, and this is what the tool actually does. And these are the arguments that are required for the tool to execute. So all of this information had to be provided in the application itself. And then when the model saw the user prompt, it understood that to answer the user's question, I need to access these tools. And this is what I need the answer to. So a tool call request would have gone via the model back to the developer, to the application itself. And then the execution of that tool occurs at the application side, right? And once the temperature in this case is returned, that response is sent back to the model, which wraps it up, which thinks about that. And if that's the only user question, it returns that to the user. Else, it does further multi-step thinking and further reasoning if that's required. So this is a nutshell about what's required to execute a tool. And one more thing I want to put out there is we thought about agents as just having LLM plus prompt plus access to tools. But now I just want you to think about and give us shot at what would an agent look like in production, right? Because our topic for today is agent from code to production. So what would a production grade agent look like? And that's going to be the next poll. So that should come up on your screen just shortly. I think a majority have answered. So okay. I think we can end the poll now. It's ended. So basically, LLM, prompt, tools, MCV server, and guardrails are needed for a production grade agent. And we said that the minimum requirement for an agent is LLM plus prompt plus tools, right? So where does MCP come in? MCP just standardizes tool access. So remember, for the LLM to know that there is a tool out there, it's hard coded in the application by default before MCP came out. With MCP, with an MCP server to be exact, this information is dynamically provided to the LLM should it ask for it. So LLM can ask that, okay, what tools do I have access to? And an MCP server can answer it for that LLM and give it access to those tools and also get those tools executed, right? So MCP server is definitely a requirement for a production grade AI agent at scale. And guardrails are basically security features that the LLM is not, giving responses that it should not be giving. either personally identifiable information is getting leaked, which should not be getting leaked, or let's say it's giving toxic or biased responses, which are definitely going to put the business at a reputation risk out there, right? So this is something to keep in mind, and we will again explore a lot of these production grade aspects when we go through this session. So now let's go through building the first agent, right? How do you actually build it? And we'll take a problem statement for this agent, which is a very simple problem statement. It needs to research around a particular topic that the user enters, basis web search. So it needs to search for real-time information and also across the web. And then whatever research has occurred, it needs to basically generate a final report out of it, right? As per the user's constraints and so on. So the user can really be very defined into how many words and what structure, what tone, what style of the output they need, right? So they can follow, let's say, the standard CoStar framework, which is context, objective, style, tone, audience, and response format, right? So that's how they can structure, let's say, for the writer. So the key requirements here are that after the research has been completed, there should be a step of human feedback, right? So after the researcher agent has completed researching about that topic, there should be a human feedback where a human should review it, and only when the human approves, then it should go for the writing stage. And if there is multi-turn conversation which is occurring via the user, if the user end user is like, continuously talking to that particular agent, it should also have memory. There should be some message history also maintained, right? So these are two of the features that we want here. Now, how do we develop it? We will explore mainly LangGraph today, but there's also CrewAI, which is very easy for prototyping and for building multi-agent systems. But the main focus will be LangGraph, which is often used in production, right? And you can build a lot of functionalities with LangGraph. So if you want to build production grade applications, LangGraph is of choice. Now, we'll go into building agents with LangGraph, but this is the overall flow of what actually is required to build a very simple agent. You need to initialize the LLM, and we will look at how do you initialize it via the gateway. And you need access to tools, right? So you also need to initialize the tools. So if you have proprietary APIs, you need to get the API key and initialize the tool. If it is public without an API key, you can directly just access, right? Typically, API keys are required for tools. So once this is initialized, right, LLM plus tools, you need to define something called the prompt, right? As in what is actually happening, what the agent is doing, and how you define it is via state, nodes, edge, and graph. So nodes are basically discrete steps when you're breaking the agent's actions, right? So we broke the current agent into the overall agent into researcher and writer. So there'll be two nodes at least here in this case, researcher node and writer node. Edges are basically representing the decisions and the transitions between the nodes, right? So when the researcher hands off the task to the writer, that's basically an edge, right? And if the human feedback is passed, that is kind of a conditional edge. Depending on the human's feedback, either it goes back to the researcher or it goes to the writer. And finally, state is how the nodes are connected to each other in the sense that how information is getting passed across the nodes, right? So it's a stateful graph that we typically build with LangGraph. So that's how you define the graph next. And finally, once this is done, you compile the graph, it's ready to run, and then you run it. So we will explore this now. And for the demo, you can follow this particular link. Let me also paste this in the chat. So this is the GitHub link that you should refer to. And when you go there, you will see this particular notebook, right? So you need to go to source, agents, LangGraph notebooks, and this particular Python notebook. And this is what we will basically walk through, right? So let me just launch this. Second. All right. So once you clone it, I'll just do a quick um, environment setup. All right, so this is how it will look like. So first thing is, as we discussed, just setting up the environment, importing libraries, loading the environment files. So some things that you need to in order to run this particular notebook are mentioned in this example, environment file. And I'll shortly show how you can access, the TrueFoundry API key. This can also be your own specific OpenAI API key or Gemini API key, whichever model you want to use. But in this case, I'm just referring to the TrueFoundry API key, which is a centralized API key where you can easily switch models, right? So that's the key functionality of this API key. Then there is the tool, which is we will be using Tably for web search. And then you can mention which model you want to use, right? So here we'll be using GPT-5 in this example. And this is specific. If you're using TrueFoundry API key, you need a gateway URL. So this is what is a sample one. And we will also need a Langsmith API key, right? So you should just follow along in this session. And just to demonstrate where you can pick up the TrueFoundry API key, right? So if you go to the gateway playground, there's just this code snippet, and you can pick the API key from here, right? But you can also give your own API key. All right. So coming back to our notebook, we initialize the LLM, and here all the requests flow through the gateway here in this example, and we set up the tools, right? Then we define the state in the nodes. So the state is just inheriting from messages state here. And we are just defining a custom class, which is research state, which has three attributes: query, which is the user query; the search context, which is what is getting outputted by the researcher agent, researcher node, once it has actually done the web search; and the final report after it's written by the writer node, right? So once you have actually defined the state, which is how information is getting passed, right? These attributes will actually store the information across the agent's entire life cycle, how it is thinking through this process, right? Then we define the agent node. So this is the researcher node, where the key things to note is here the researcher will by default always do a web search, right? So this is not optional. This is part of its task. So that's why it's directly within the node. And then there's a persona as well. And there's an instruction. And finally, we are just putting it all together, and it's returning the search context, right? So this is the researcher node where we are defining that it will take the state as an argument, and it will also return the state outside, right? So this is the researcher node. And at the end of this node run, search context is basically filled. Then you have the writer node definition, where again it's taking as input researcher state, and it's also outputting research state. And the key output here is the final report, right? So it has a prompt, which is defining what it should be doing. It has a persona as well. So I have just separated this out, right? So this is the persona, which is the system prompt for the writer, and this is this is the instruction, right? Uh, Overall, and then it's just going to execute that when it is called, right? So this is the invoke. All right. So the two nodes have been defined, which is the basic agent without the human in the loop. Currently, there is no human node. Currently, it's going to just execute it by default. There's not going to be a human feedback or memory currently. And then you finally you create the graph. So this is how you would create the graph. We're just initializing a workflow, right, which is a state graph. You will be adding nodes here, which are the two nodes, and just defining the flow of the graph, which is it should start with the researcher node, it should go from researcher to writer, and then it should just end at the writer, right? So it's a very simple workflow, agent workflow in this case, right? Um, so when you run it, it's basically going to be that you need to initialize a state and just invoke that. And giving you a example of how this is going to look like, the query is latest developments in quantum computing hardware in 2025. Keep response limited to 100 words. So this is my user prompt, and this is my response, right? Latest developments are basically mentioned. So again, we have walked through a very, very basic agent, and hopefully you have followed so far, right? If you're comfortable with LangGraph, this will be pretty easy. But even if this is first time, few key things to again go over. The first thing we are doing is initializing LLM, initializing the tools, which is just the Tavily tool, right? Remember, we are using the Tavily API key, which is being used behind the hood, defining the state, defining the agent functions, which are the nodes, and then just defining the flow of it, right? And then running it. All right. So let's now see how you do this for CrewAI, right? And we'll also build this simple agent with CrewAI. So CrewAI is again simpler than LangGraph in terms of how the agents are built, and it's pretty powerful for building multi-agent systems, right? Where you do not really want a lot of control. So with LangGraph, you have explicit control over what things you can do with the graph, but with CrewAI, a lot of it is abstracted out and it's simpler to use. So the overall flow still remains the same. We initialize the LLM and the tools. In this case, instead of the graph definition, you have to do the crew definition, which consists of three things: the agent, the task, and the crew. So what is an agent? Agent is basically an object within CrewAI, right, that you have to define with a role, a goal, and a backstory. At least these three things should be there to define the agent. The task is also needed, which is a specific assignment completed by an agent, and the task description and the expected output are needed to define the task object, right? And finally, the crew is how it's assembling the agents and the tasks. So you have, let's say, 3 or 4 agents, and each of them have a task. The crew basically sequentially defines how this should be executed, right? So what is the strategy for task execution, agent collaboration, and the overall workflow? Right? So this is how CrewAI works. And again, you can have back and forth between the agents. So the agents there can be complex workflows where, agent one is going to agent two, but basis some condition, agent two is going back to agent one. So that can also be done. And finally, we will test it. So let's see then this in action. And for this, you will need to navigate to again source, agents, and then CrewAI, and then notebooks, right? So let me just open it quickly here. The first few things are the same, right? LLM and Tavily search. And I have one more tool here, which is the file writer tool, which is basically from CrewAI tools. So we have one nice tool in CrewAI here. And then just note the syntax, it's slightly different. You need to have a role, goal, and backstory for the agent definition. And here we also have tools, so you need to mention that, mention the LLM as well, and a few other parameters here, right? So allow delegation is whether it can delegate this task to another agent or not, right? So that's allow delegation. Similarly, we have the report agent, which is the writer agent. And we have two tasks. One is for research and one is for the reporting, which is the writing. And you can explicitly mention these things here. And then we just initialize the crew and we just assemble the crew in a sequential manner in this case. Right, so this is for CrewAI. The syntax is slightly different, but you can still accomplish the same thing in this example via CrewAI. Right? So I'll not walk a lot over CrewAI because I want to cover other advanced features. So let me move forward now. And by this time, you will have a good sense of what agents are, how do you build agents with LangGraph and CrewAI. At least you have the high level structure. But now let's walk through certain features that we talked about, like human in the loop and memory. So within LangGraph, right? In general, what is memory? It's basically enabling that persistence across the conversation, right? And probably across users in a larger sense, right? So let's say as a user one, you are having chat number one, you are talking, having multiple prompts in that chat session, and it's basically able to reference the previous conversations as well within that chat session. With the conversation within that chat session is kind of available to that LLM. But let's say you open chat two, you open up a new session, and you start interacting with the agent, right? Will it actually reference the first chat session? Probably not. So what you need for that to occur is you need long-term memory. Long-term memory basically refers to user-specific or even application-level memory, which is kind of persisted across conversations, across even users, right? If it's an application level, that memory will be persisted across users. So that's kind of long-term memory. But short-term memory is something which is very, very relevant and which is almost always a necessity is within the same chat session, the memory should be preserved, right? So it's not that I prompt once that my name is Anant and the second prompt is like, what's my name? It forgets my name. That should not be occurring. So this kind of enablement is done by short-term memory. And in production, it's a good practice to always write the memory checkpoints to a database, right? Instead of having it in memory, it's always a good idea to write it to a database because for any technical reason, let's say, that session is disconnected. When it connects back, it needs to refer to certain checkpoints so that it can just resume the conversation again. And it's important for a good customer experience. So this is how you can think of a short-term memory. It's just that, what was the human message, what was the AI message. That alternate sequence is kind of preserved by the thread in this case, which uniquely identifies this particular session, right? And each of these messages at some point are getting checkpointed to that thread, right? Which is just a unique identifier. And long-term memory is basically the same thing occurring over multiple users that's getting stored somewhere. So we will walk over short-term memory and we'll see that in action now. So let's go to back to the LangGraph notebook. And it's a very simple way in which you can enable memory. And we'll focus on short-term memory enabled by thread level persistence here. So there are two ways in which you can do it, right? One is in memory and the other one is database backed memory. So for an in memory, you just need to, call the LangGraph checkpoint memory module and just import in memory saver, initialize that. So this will act as your checkpointer, right? And this is what you need to mention when you are compiling the final graph. So after all the definition has been done of the nodes, state, and the graph and the edges, basically all of it, when the compilation is occurring, you need to mention this checkpointer. And the thread ID is separate, which you need to mention in a config, right? So this is how you can enable memory. And at runtime, when you're invoking, the LLM basis the prompt, which the user is asking, you need to mention the thread ID as well, the config as well. So the graph remains the same, nothing changes there. The only thing that changes is when the graph is getting invoked, right? It needs to get invoked with this particular configuration, which basically has the thread ID in it, right? So this is the key thing to keep in mind for memory is that when you're compiling the graph, you need to mention that it should checkpoint, right? So it's within kind of the compiled graph, the checkpointer is contained there. And while invocation, the thread ID needs to be always mentioned, right? So in the application code, this is how you can easily enable memory. And this is in memory. All right. For a database backed memory, it's just an extra step where you need to basically initialize SQLite in this example, and you can also have some external DB that you want to write to. And that's how you can connect to that external DB and initialize a memory, here in this case, SQLite saver. And the remaining steps remain the same. So each time the checkpoint is done, right, it will save that to the external DB. In this case, it is a local DB, so it will be saved there, right? So if I show you the checkpoints, right? So I think for some reason it's not opening, but you will have the checkpoints available as well within that particular folder, right? So the file is basically existing. So after each node execution, this checkpointer is basically appending new checkpoints and saving the state. So the state accumulated till that point, till the point the graph has run, is basically getting accumulated and it's getting saved per that checkpoint per that thread. right? All right, so this is about memory. This is a simple example about how you can enable memory. And the next thing we are going to cover is human in the loop, right? So this is where you want to pause the agent's thought process for human feedback. And this is especially important for use cases requiring human review, right? Especially in production, definitely this is something that you would want if you have a critical use case which requires human review, right? Which is very sensitive use case. Before showing something to the user, you need, a review in certain cases. So reviewing tool calls, for example, before execution, if there is sensitive data involved, right? You can also modify the tool call, what the LLM is going to request for. All of that can be done here. You can validate LLM outputs before finalization, before it's shown to the user. You can also have the agent ask for clarification, right? If it's trying to perform its task, but it's not clear about certain things, you can ask it to stop, ask for the user's question, and assimilate that particular answer of the user back into the overall flow, and then go ahead with the task execution. So that can also be done. And this is just what I'm demonstrating here. There is like these three kinds of things. This is where conditional upon the human, it can be either approve or reject, and it can have a conditional edge, meaning that either node 1 can be called or node 2 can be called. So they'll have different flows through the graph, right? Review and edit state is where the human can come in and it can edit the state, right? So it can also edit things as well. And reviewing tool calls is where before a tool is getting executed, a human is sitting in between and actually validating that that's the right tool to call, that's the right arguments to mention to that tool, and things are not breaking, right? Because what can happen is, think of a very powerful tool out there, and the LLM is just generating junk, and it's basically causing a security issue where the arguments that the LLM has mentioned for that tool call are something completely wrong, right? Which can actually break the tool, right? So the human in those very sensitive cases has to review the tool call and what arguments are getting passed to that tool, right? So this becomes important. Now, how do you actually implement this within the agent? And again, this is something which is very important for a good use case. Most of the production use cases would require some kind of human in the loop were things to fail, right? So this is always a requirement. Um, so here we will be using interrupt. And the good thing about interrupt is it's something provided by LangGraph. It pauses the workflow and saves the state to pick back up later. So it does that. It recovers from crashes and handles restarts well. And basically, overall, it's the method of choice for human in the loop, right? So what you need to do here in this case is I've changed a few things. First thing I've changed is the state definition, which is basically now an annotated object. So the search context, right? Remember, the first flow was just a one-shot flow. There were no iterations involved because the researcher were always going to the writer and the writer was always ending the flow. In this case, what can happen is once the researcher node has completed, the human can reject the answer. It can give a negative feedback and it'll go back to the researcher node. So the researcher node needs context of what happened first that the human actually rejected, right? What was its first output? That's why we need to basically have a list of messages. Similarly, we need a list of messages of the human feedback. And here, this is a reducer function, which is just appending the response to this list, right? Okay, so that's one thing. And then basically, we need some changes in the researcher node as well. So let me skip some of this. I'll just go over we also need to define a human node where we are implementing the interrupt function. And this is what you will see in action when I just show a demo of this to you. All right. And we're just compiling the graph as is, nothing changes there. But one more thing I think I want to point to is what happens after interrupt, right? So let's say the human gives a feedback. We need to also direct where the human node should go, right? And remember, we have built a stateful graph so far. So it's an edge based graph so far, right? Where we have defined the edges. But in this case, with interrupt, what you can do is you can also use something called a command function, and you can say that if there is no user feedback, which is basically if the user feedback is done, go to writer node, else in all other cases, go to researcher node, right? So this is a kind of an edgeless workflow that we have developed. And that's why if you visualize it, you're seeing the edges here, but you're not seeing an edge with the writer node, right? Because it's an edgeless workflow, but it will still work out. So let me now actually go ahead and show how this is working. I'll skip some of the code here in the interest of time. And this is again available. You can walk through it. So let me launch. Second. All right. So let me just launch the LangGraph app locally. So I will just activate the virtual environment. And we'll just see this in action. All right, so this is something that's launched up, and you just need two things here, which is there in the code. You just need, a LangGraph JSON file, which is mentioning what script needs to be referred to. So this is something which is easily available. Now, let me give it the query again. Latest developments in quantum computing hardware in 2025. Right, and if I submit it, okay, I think I've been logged out. All right, so it's going over the researcher node that you can see now. So it also visualizes and gives that to us. So right, so it's thinking through it, and once the research has completed, it will basically prompt us here itself, right? So it will interrupt and it will ask us for a question. And just for reference, while this is running, what script this is referring to is nothing but we have defined a script. We have just, for productionizing, you need to define a script. So we have defined this particular script. We have just wrapped the code in a script, and this is what it is referring to, right? In order to execute. So this is our final app that it is basically referring to. So now you'll see that, there's an interrupt where it will ask us to provide a value, and I'll just say done. And it will go ahead, go to the writer node now, even though it's not part of this edge-based graph, right? This is an edgeless workflow, and it will finally end after that. So it will complete this. All right. So this is how human in the loop works. And you'll see the output has been generated and it's good. All right. Okay, so now let's switch gears and let me skip streaming because it's just very simple. You can also stream the output, which we have done actually in the code for human in the loop. So let me skip this part. It's very straightforward, right? And you can go over the code here in this case. All right. So with this, let me launch one more poll for the session, and let's have that up. Let's take a few more seconds to complete this. Log in your choices. All right. So let me share the results. So the audience is basically split, but the majority is the second option, right? So what are we looking at? The first one is context loss, which is forgetting the details, right? And that's typically solved with memory, right? Because it cannot be done via the LLM, because remember the LLM by default, it's just a model, it's just an intelligence engine, it's nothing else. And streaming is also something which cannot really solve for the context loss, right? Streaming enables, it'll just continuously stream the output. It will not help with that. Second one is rigid flow, no multi-step planning. That's obviously orchestration, right? Because that's something that has to be per how the agent workflow is kind of built and how it is basically thinking through things. The third one is high latency, long awkward pauses, right? So if you ask something to an IVR agent and it waits for 10 seconds and then responds, obviously it's a very, very long awkward pause versus something it answers in, let's say, 3 or 4 seconds, right? So streaming can help with that because it will think through and it's also generating output, right? So streaming will help with that. And finally, security risk will be solved with human in the loop. So just by elimination, obviously the second one is the right answer. All right. Now let's switch gears. Now we have understood how to build agents and look at advanced capabilities. How do you deploy the agents, right? So let's go to this particular file, which is server.py, and I'll just walk through how do you actually wrap this agent behind a fast API endpoint. And this is very important because this is the point where a lot of developers and teams actually face a roadblock or are not very clear of what actually is happening. So first question is why fast API and why not something like Flask, right? So fast API is good because it's asynchronous, which means it's very good for input output kind of tasks, right? So remember what agent is doing. It's hitting the LLM, it's getting an output. It's or what the agent is doing. The agent is basically comprising of LLM. So there are LLM input output calls going on. There are tool input IO calls going on, and things like that are happening, right? So for that, asynchronous workflows are best, and that's why Fast API comes in. And again, what we're doing here is the key things to remember is you need to initialize a fast API server, right? So we are mentioning the title, the root path, and the docs URL where you can actually see the fast API docs. You will see this in action shortly, right? I have also modularized the agent. So just importing this run agent. And if you look at this run agent, it's again an asynchronous function, right? Which means I have just done an async def. So let me open that here. So just notice that because we are using fast API, we are doing async here. And again, you need an await here and you need a invoke, right? That's pretty much it. So we are doing that. We are adding a CORS middleware, right? So this is standard. We are defining a health check endpoint, which means that this particular server at this particular endpoint, you can get what if everything is okay or not. So that's what we are defining here. And I'm also defining a pydantic model. Now, pydantic is just for the types, checking whether the user input is string or not, right? So it needs to be a string. And finally, this is the primary endpoint, which is the chat endpoint, which basically returns the output, right? So it runs the agent and just returns the output. And again, this is an async def because this is asynchronous and we need an await here, and that's it, right? So in terms of the syntax, this is primarily how you build and wrap the agent. There is an agent.py and this is the server.py, which is the fast API server code, right? So this is the first thing to keep in mind. The second thing to keep in mind is you can either deploy it via the Python code directly, or it's better if you can create a Docker file out of it, right? So this file will be used and accordingly the Docker image will be built, right? And the main command to run a fast API server is uv run uvcon and then the path, right? So which is this module and colon the name of the particular server, right? So we have defined it as a app variable. So this is that, and the host should be such that it is running at all kind of URLs, and the port is 8000, right? Which is the standard fast API port. So I'll just show how you can deploy this on TrueFoundry and how TrueFoundry makes it really simple to deploy. So there are very few steps involved in deployment. So this is the deployments tab, and within this I've already deployed it. So let me just show you how you can actually deploy it, right? So these are some of the configurations you need. Just mention the name. We are going to deploy this from source code via the Docker file. So here, if you mention the repo URL, it'll automatically pick up the branch name and the latest commit ID. And you can just mention the path to the Docker file, which is this particular Docker file. And that's it, right? Some additional configurations is you can mention, this is the endpoint which it automatically comes up with. And we are mentioning the port as 8000. And you can also configure the resources, whether you want this particular deployment to be done on CPUs or GPUs. And if GPUs, then what configurations, which of these. You can also mention things like CPU request limit, memory request and limit, and storage request limit. The capacity type, the machine, the instance can also be mentioned. Is it spot or is it on demand? Typically, this is a good option. And then some environment variables need to be mentioned here, because remember, these are currently in our .env file when we are doing it locally. But when you're deploying it, you need to mention some of these API keys and the environment variables. Now, what TrueFoundry also enables is you can have secrets stored. Like API keys are sensitive information, so you probably do not want to just copy paste it here. So we do have secrets where you can actually, store that API key in that secret and just refer here. Right? So you can create that, refer to that, and you're good to go, right? And there are a lot of other parameters that you can actually tune, but we'll skip these for now. These are the minimum required to in order to deploy this particular agent, right? So let me just redeploy this. And let's see what's happening, right? It'll take a few seconds to actually deploy. So it's just basically getting that GitHub code, right? It's building and getting the Docker image ready. All right. So this is pending. This will shortly be in running, and we will see when that's ready. So in the meantime, while this is coming up, let me also show you how you can deploy a simple fast MCP server, and we'll take a few minutes, and then let me close with questions. Right. So for MCP, again, you can wrap this agent, that run agent function into as an MCP tool, basically. And the benefit is obviously it's wrapped within MCP, so it's going to be discoverable by other agents, which are going to probably, you want to talk to it. So here we'll be using FastMCP, which again uses, a similar asynchronous workflow. And you can just define something called MCP tool, which is the tool decorator. And the same thing where, you're just calling the run agent function, the main agent function, and you're good. And there are a few other things, but I will skip that. But the main thing is you need to define, wrap the agent within an MCP tool. And then finally, there are few things in order to run the MCP server, right? So the transport is over HTTP because this is a remote MCP, and that's it. Right, so you can deploy this in a similar fashion on TrueFoundry, where you need to go to deployments, add a service deployment, and you are good to go. So now we see that our agent deployment is running, and you can also see here in Open API, you can test these particular endpoints within the TrueFoundry platform itself. All right, so this is already integrated. once you provide that reference, and you can test it out. So we are good to go. This has already been deployed, right? So let me show you an example. I'll go to chat, try it out. And I've deployed a simple agent, by the way, without human in the loop here. All right, so it's running. It will take a few seconds to run. And we can also see what's happening, right? You can see the logs, you can see the metrics, you can see, different kinds of metrics here. You can see the CPU usage, memory usage. All of that is now spiking up because at this time we are running it. You can also see the key events which are occurring, right? And shortly it'll give us the answer, right? So it'll take a few seconds. Let me skip that while it is doing it, and briefly walk over the last few part, which is like monitoring, guardrails, and configurations. So let me show where you can actually monitor the activity of the agent. So you can go to the monitor tab here, right? Here you have a bunch of model metrics. For example, we can see requests per second. And let me just filter this to a model name that we are using and just apply this, right? So this is what we are using currently. And you can see the request per second, you can see the request failures, latency per output token at different percentiles, right? Because remember, each prompt output pair will have a different latency, right? No two prompt output pairs will have the exact same latency. There will be slight minor variations, which is where you want some percentile understanding of, okay, 99% of the request had a latency lesser than this. Similarly, if you see this, P90 will be different and P50 will be again slightly different, right? You can see the cost of inference, input output tokens, and a lot of the latency metrics. Similarly, you can also see this at other granularities, like at a user level, at a team level, and so on. And similarly, we have other metrics at an MCP, for an MCP server, like request per second, request latency, request failures, and so on. So this is the monitoring part where you can do a lot of things, and this is all OTel compatible. Then you can also have guardrails, right? Which is what we talked about is very important for a production grade agent. You can have these guardrails, and you can just configure this as part of the agent definition, right? And finally, there are a few controls that you can also mention. So we'll cover this in a separate session. But you can do a lot of things around how the agent is hitting LLMs, and how often is it hitting LLMs, because it's iterative. So it might just hit LLMs again and again, right? And it'll shoot up your costs. So you want some checks on that. All right. So with this, we are also at time. Let me open the floor now for question and answers, and we can take some questions which are there in the chat.
Great. Thank you, Anand, for taking the session. Yeah, guys, we are here for